Okay, in this video we are going to be going through the second half of section 16.3, conservative vector fields. The first half dealt with defining what a conservative vector field is, how do we verify that something is a conservative vector field, and then how do we find that scalar function phi. That is called the scalar function. Now, in the second half of the section, we're going to be looking at line integrals and conservative vector fields and how they go together, how they work together. So it starts out with Theorem 16.4, the fundamental theorem for line integrals. And we're given f a conservative vector field on an open connected region R, and R2, that should be, R2, the bold one. I just couldn't type it easily. And then there exists a potential function phi with f equal to the gradient of phi, so that means that f is conservative, if and only if the line integral over c of f dot t ds or of f dot dr is equal to phi of b minus phi of a for all points a and b in R and all smooth-oriented curves c from a to b. Okay, so they go through part of the proof in the book of this. I'm not going to do that in these notes, but that's the what we'll be primarily using here is this part of the theorem. So it kind of refers back to setting up line integrals from the last section, and then relating that to conservative vector fields. Now let's look at an example using this theorem. This is example 3 from the text. We are going to, it's called verifying path independence. So we are given a potential function phi, x squared plus y squared over 2. We're given a gradient field f, x negative y, and we're given two curves. C1 is cosine t sine t, but only from 0 to pi over 2, so note that that's a quarter circle. And C2 is a line, r of t equals 1 minus t comma t for t from 0 to 1. And then the thing to note also for both of those curves with the specific bounds, the t-bounds that were given, they go from the point A, 1 comma 0 to the point B, 0 comma 1. And I didn't write this part out, but what we need to do is evaluate the line integrals of f on C1 and C2, so we have two line integrals to evaluate, and show that they are both equal to phi of b minus phi of a. So essentially we're verifying that theorem that we just looked at. All right, so our first step, well, let's look at our line integral for C1. So let's deal with C1 first. And we need to compute r prime of t. That goes into our line integral formula. So that would be negative sine t, comma cosine t. And then we also need to write our f, our gradient function, in terms of t. So f, which is equal to x negative y, is really, in terms of t, going back to the original r function, cosine t, not the derivative, comma negative sine t. Okay, so there's our first step, and those two pieces get substituted into our line integral. So we have the line integral over c of f dot dr is equal to, let's see, I'm going to write it one more time, the line integral over c of f dot r prime of t dt, which now substituting everything in, this is the integral from 0 to pi over 2 of cosine t, comma negative sine t, dot negative sine cosine, negative sine t, cosine t, and I've just got to squeeze my dt in at the bottom there. Okay, so the first vector there, that's my f vector, my gradient field, and then the second vector, that's the r prime. Okay, if you go through that dot product, the dot product isn't the time-consuming part, but you go through the dot product, and use an identity, and what you end up with, so I am skipping a couple of steps here, I'm not going to go through the whole dot product. The integral from 0 to pi over 2 of negative sine 2t dt. Negative sine 2t dt, and that is a 2. Okay, so it would be the dot product, and then using an identity, 2 sine theta, sine of 2t equals 2 sine t cosine t is involved in there somewhere. And then if you evaluate that integral from 0 to pi over 2, you get negative 1. Boom. So that's the first thing that we needed to find, okay, for our C1 region. Next up is C2. So I'll do this one in a different color. Let's see. C2, we've got to look at the same things for that region. So for C2, our r prime of t is constant, negative 1 comma 1, because r of t was a linear function. And then our f function becomes, so remember that was x negative y, that becomes 1 minus t, 1 minus t, comma, negative t. Okay, and we plug both of those things into our line integral. So in this one, it's the integral from 0 to 1, 1 of 1 minus t, 1 minus t, comma, negative t, dot, negative 1, comma 1, dt. Again, this is my f, this is my r prime of t dt. And the bounds of the region come from the t bounds that we were given way back at the beginning of the problem. Evaluating that integral, right, you do the dot product first. That dot product results in, you get negative 1. So it's the integral from 0 to 1 of negative 1 dt, which is just negative 1. Boom, right there. So we got negative 1 for both of them, which again, we should have. Okay. The last step is to verify the last part of the theorem, that phi of b minus phi of a is also equal to, well, in this case, it should be negative 1. So our phi function, remember, that was x squared plus y squared over 2, again, way back from the beginning of the problem. So if I take my phi of b minus phi of a, well, you get, well, let's see. What I would do is I would plug in the point 0, comma 1. That's my b point. Minus phi of 1, 0. And that results in, you get, what is it, negative 1/2 minus 1/2. Just plug those 2 points into the phi function. And you add them together, and lo and behold, you get negative 1. So we got negative 1 for each, which, again, verifies that the theorem, it applies to this conservative vector field. Okay, one more theorem and one more example to go in the section. The last part we deal with line integrals on closed curves. So the last 2 curves were both open. One was a quarter circle, one was a line segment. In this last part, they're going to be closed curves. The one thing with notation that is just ever so slightly different, when we have a line integral for a closed curve, we have an integral sign with our c just like before, and it would be of f dot dr. So nothing is different there, f dot dr, but the integral sign just gets a little tiny circle in the middle of it, and that just denotes that it is a line integral on a closed curve. Okay, and then theorem 16.5 here, that one is, logically, it should hopefully make sense if you remember a little bit of Calc 1. Let R in R2 be an open region, F is a conservative vector field. On R, if and only if, the line integral of f dot dr equals 0 on all simple, closed, smooth curves, or smooth oriented curves C in R. So the reason that hopefully should make sense, if you remember Calc 1, if you have an integral from A to A of a function, right, the area under that curve is 0. So if your starting point and your ending point are the same value, the integral evaluates to 0. So if we have where's my pointer? There it is. If we have a closed curve, well, then my starting point and my ending point are going to be the same value. So that integral, that line integral, should evaluate to 0. Okay, in this last example for this section, we have to evaluate a line integral, the gradient of negative xy plus xz plus yz dot dr on the curve, r of t equals sine t cosine t sine t, so we're in R3 for this example, and our t bounds are from 0 to 2 pi, so you can see there we would have a closed curve, start at a point and end at the exact same point. So our line integral should evaluate to 0. But what the example says is without using Theorem 16.4 or 16.5. So we're not allowed to say that it's 0, done. We actually have to evaluate the integral. So what we'll start with is our vector field f, and our f is equal to the gradient of what's inside of that integral, negative xy plus xz plus yz, and that gradient gives us, if you take the partial derivative with respect to x first, you get negative y plus z, and then the partial derivative with respect to y, you get negative x plus z, and then the partial derivative with respect to z, you get x plus y. X plus y. Okay, then the next step, we've got our gradient of f now. We're going to take our curve and find r prime. R prime is cosine t, negative sine t, cosine t. And those two guys get substituted into our integral. So what we have for our integral in this one, now remember it is an integral over a closed curve. So we have the integral sign with a circle on it, integral over a closed curve of f dot dr is equal to, this is going to be the integral from 0 to 2 pi, and I'm still going to have that little circle on there. And now when we write our f function, I'm not going to write negative y plus z, negative x plus z, and x plus y, right? Because this integral is going to be in terms of t. So this one gets a little bit ugly when you substitute everything in terms of t. So your I component is negative cosine t plus sine t. That's negative y plus z. Negative cosine t plus sine t. Your j component is negative sine t plus sine t, negative x plus z. And that would give you 0 in the middle there. And then your k component is sine t plus cosine t. So there's my vector f. That's a little ugly. And then dot, the dot product of that and your r prime, which is cosine t, negative sine t, cosine t. And all that gets integrated in terms of t. Now, I'll leave it up to you to go through that dot product, save a little bit of time. The middle term, it would be 0, so you wouldn't even have to write that part down, but there would just be some distributing and some simplifying there. But what you would end up with, again, after applying an identity, is you would end up with the integral from 0 to 2 pi of sine 2t dt. Again, you would use an identity similar to the previous example. And that integral, with that antiderivative, is negative 1/2 cosine 2t. And that gets evaluated from 0 to 2 pi. And lo and behold, when you plug in the top bound minus the bottom bound, you get 0, which is what you should get, again, according to the theorem. Okay, so that is it for section 16.3. Hopefully you started working on some of the problems. Hopefully I will be better by Friday and I will not be canceling class again, but hey, who knows? All right, shoot me an email if you have any questions or come with some questions on Friday. Thank you for watching.